Hello everyone, I Srilata and my teammate Madhusudan, as part of our course project in LTE and 5G communications, have done various channel sounding measurements in indoor environment scenarios like empty classroom and a corridor, and has observed and analyzed how having line of sight between transmitter and receiver helps in the signal strength, and how obstacles affect the signal strength in 5G communications. And through this presentation, we present our results. With the happening Internet of Things, autonomous driving, the demand for data is growing exponentially. This rapid growth is saturating the LTE band completely and encouraging us to use millimeter wave bands. 5G will use spectrum in the existing LTE frequency range and also in millimeter wave bands. 5G's performance targets high data rate, reduced latency, energy saving, cost reduction, higher system capacity, and massive device connectivity. With increasing frequency, various effects like path loss, diffraction, penetration loss increases. Millimeter wave frequency band is highly influenced by obstacles around the channel, as a small obstacle in the line of sight will impact the signal strength. The proposed method for overcoming this issue is the use of beamforming with sector steering. Beamforming helps in propagating of the reflections from obstacles and improving the connectivity. The wireless communications are significantly affected by the environment surrounding them. The various obstacles creates multiple paths between the transmitter and the receiver with different time variances and attenuations. We can exploit the multi-paths to increase the channel capacity and quality of service in MIMO. MIMO, multiple input, multiple output, is a way in which we use multiple transmitter and receiver antennas to send multiple data signals. In order to evaluate effectiveness of these multiple antenna systems, a measurement of the radio environment is needed. Channel sounding is such a technique that can estimate the channel characteristics for the simulation and design of antenna arrays.
The goal of our project is to demonstrate channel sounding in various indoor environments and to study the effect of obstacles on millimeter wave in these environments. Let's look at what is the hardware which we have used for our measurements. We have made use of mmWave transceiver system from National Instruments. mmWave transceiver system is a research platform for channel sounding measurement experiments, and it is integrated with LabVIEW software, which helps in interacting with the system very easily. And then the system is built on a PXI platform, which offers basically different flexible modules, which helps in reconfiguring the system very easily for different modes of operation and things like that. And mmWave transceiver system is also composed of transmitter and a receiver chassis, a controller, a clock distributed model, digital to analog converters, analog to digital converters, IF up converter, and IF down converter, which we will see in the upcoming slides. And there are different modes of operations also, like unidirectional mode and multidirectional mode. In unidirectional mode, it has a transmitter and a receiver system, which can be placed at different distances and different environments also, and that is the thing which we have used in our environment. So this is the block diagram of mmWave transceiver system from NI. As explained previously, it consists of digital to analog converter and analog to digital converter. As seen from the left side of the figure, we can see there are different FPGA processors, and it has digital to analog converter, and that is in turn connected to mmWave transceiver system, transmitter basically. And if we see the right hand side of the system, it has analog to digital converter, and it had different FPGA processor and then IF converter also, which is directly connected to a receiver in the system. And this is the flow diagram of transmitter as well as the receiver. The top part is for the receiver. We have made use of a horn antenna for our measurement purpose, and which is directly fed to the receiver. of the transceiver system, and then the signal from the receiver is fed to IF down converter, and then to the baseband receiver, and then to FPGA processor, which is also integrated with LabVIEW software, and from where the measurements will be collected. Basically, the data will be extracted from there. This is the receiver part, and below part is for the transmitter, where the processor information is directly fed to the baseband transmitter, and from the baseband transmitter it will be it will be fed to IF up converter, and then to the transmitter system, and then to the antenna, which is basically again a horn antenna which we have used. Now let's look at how we use this hardware system and how did we set up this hardware. Transmitter and receiver with horn antennas were basically mounted on a rotating gimbal so that it helps in taking the measurements at different azimuthal as well as different elevation angles. The distance between the receiver and the transmitter were varied to collect different channel responses. This collected data was processed for studying the effect of obstacles on the millimeter wave at different azimuthal as well as elevation angles.
Following are the different scenarios which we have used for our channel measurement. Number 1. Transmitter and receiver separated by 18 meters with line of sight and inside a closed room. The other set of measurements we took in a corridor in which 3 of them are with varying distances of 25 meters, 75 meters and 150 meters with line of sight, and the last one is with non-line of sight and of distance 11 meters. The transmitter and receiver are placed on rotating gimbals, which allows us to transmit and receive data in various elevation angles and azimuthal angles. Initial calibration is as follows. Due to the presence of multiple obstacles and different materials in between the transmitter and receiver, and due to hardware issues, the channel response might have distortions in the signal which needs to be eliminated before performing the measurements. This is taken care by syncing the clocks between the transmitter and receiver. Clocks between the transmitter and receiver were synced by connecting them directly through a calibration cable. After the calibration, the cable is disconnected and the transmitter and receiver are moved to desired distances for measurements. To protect the transmitter and receiver from any spur or spike signal of high power, an attenuator of 40 dB is used. Now, FPGAs at the transmitter and receivers are reloaded, and connection between the transmitter and receiver is established through Wi-Fi. The time of flight of the signals is adjusted manually to align it with the distance between transmitter and receiver. Gimbals at transmitter and receiver are adjusted to align and have line of sight between them, and then we can take the measurements. In the scenario 1, the transmitter and receiver are placed at diagonal corners in a classroom and the measurements are taken. They both are aligned at 45 degrees so that they have line of sight between them. The right hand side plot represents signal strength of various multipath components with respect to delay. Basically, we group all the multipath components with the same delay and then plotted the best multipath component which has a maximum power in this plot. The multipath component with the shortest delay has the best power, and as delay increases, the multipath component arrives after getting reflected various times. The x-axis in the graph represents delay in nanoseconds, which is obtained by multiplying delay sample count with 0.6. Until 255 seconds, we observe that the signal strength decreases with the increasing delay, but At around 255 seconds, we see that the signal strength is again good, and then the plot continues the trend. This behavior should be because of the reflective properties of the path of the particular multipath component. Basically, it should be a good reflector and shouldn't have attenuated the signal much. This plot represents the heat map for the scenario. The x-axis represents angle of departure at transmitter and y-axis represents angle of arrival at receiver. Both of these are azimuthal angles. In the right, we can see how the color bar is used for this plot. Basically, the signal with highest strength is indicated in yellow color. If we observe the plot, at angle of departure minus 40 and angle of arrival minus 41, we see the strongest multipath component, which is as expected, and the remaining grids represent various angle of arrival and departure for various multipath components. In the scenario 2, the measurements are taken in a corridor where the transmitter and receiver are placed at 25 meters from each other, and so that there is a line of sight between them. In the previous scenario, the measurements are taken in an empty classroom where there is no human interference. But in this experiment, there was human interference during the measurement duration. That is clearly visible in the right hand side plot. Here, the signal strength decreases with the delay increment, but we see few random behaviors in this plot, which is because of the human interference. The heat map for this scenario shows that at -2 angle of departure and at -2 angle of arrival, we have the best signal strength for that particular multipath component. This is clearly visible because they both are in a straight line to each other.
So this is our next scenario where we carried out this experiment in a corridor by separating the transmitter and the receiver by a distance of 75 meters. And this graph actually shows, I mean, the x-axis is 0.6 times of the delay, which is actually in nanoseconds, and the y-axis actually shows the strength of the channel in dBm. As we can see, initially, since there was a line of sight existing between the transmitter and the receiver, we have very good strength of around -50 dBm in the beginning, and then as the graph moved towards the right side, due to the lots of obstacles in between transmitter and the receiver in the corridor, there are lots of distortions in the power. This is the heat map for the scenario where we have angle of departure in azimuthal angle and then angle of arrival in azimuth angle and the strength in dBm all put up in a single map. Since there was no line of sight existing between transmitter and the receiver in the beginning, we just made an initial adjustment of -2 degree tilting at the transmitter as well as the receiver. So that is the reason we can see at -2 degree of angle of arrival and -2 degree of angle of departure, we have maximum strength, which is of -55 dBm, since there was a direct line of sight. And then due to the lots of distortions, as I have explained in my previous graph, this is evident in this particular graph where there is lots of blue region. Blue regions corresponds to -100 dBm strength, which is very weak. Only at particular angles, as we can see, 167.98 degree of angle of departure and then 0 degree of angle of arrival, there is around -60 dBm power. This is our next scenario where the distance between the transmitter and the receiver is 150 meters, and this is also again carried out in a corridor. And then again, the graph shows x-axis has a 0.6 times delay in nanoseconds, and then y-axis is strength in dBm. Initially, there will be a good line of sight, and hence the delay will be very less for the signal. And then we can also see around minus 56 to minus 58 dBm of strength in the signal. And then as the graph move towards the right side, there are lots of distortions, and then due to multiple reflections, the signal might have good strength. That is evident from the graph. And this shows the heat map for the scenario where during the initial line of sight of 0 degree and 0 degree, there is a very good strength of minus 55 dBm. Also at 0 degree and minus 167.98 degree, there is a good strength of minus 55 again. And then since the distance is very much, and then lots of reflections and lots of distortions in the middle, we can see that from 40 degree to 100 degree of angle of arrival, and then 60 degree to 160 degree of angle of departure, the path is entirely blue, which is evident that there are lots of obstacles and the path was not so clear. This is our next scenario where there was no actual line of sight between the transmitter and the receiver, and they both were separated by a distance of 11 meters. And right side, you can see the same graph where initially the power was very good at around 55 dBm, and as the signal traverses towards the right side of the graph, the strength of the signal also decreased. This is the heat map for the scenario, and as we saw in my previous slide, there was no line of sight existing between the transmitter and the receiver, and that is evident in this heat map, as we can see in 0 degree and 0 degree. Since there was no line of sight, there is no signal strength at all. And then as we move down like 60 degree and 80 degree of angle of arrival, and 20 degree and 25 degree of angle of departure, there is a region where there is good strength. That is because the signal is reflected through the wall and it reached the receiver at the other end. So this shows that the signal strength is very good at certain different angles without an on-line of sight also. So to summarize as a whole, what we have observed in our experiments is that even though there is no line of sight at the beginning due to multiple reflection, the signal strength was observed very good as we saw in our final scenario. And then when the distance is less between the transmitter and the receiver, and since we carried out in a closed corridor, the signal strength was good. As the distance increased, there were lots of obstacles in the middle, and then due to the obstacles there was reflections happening with the signals, and then the strength of or the power of the signal decreased. So